We're now going to conclude our presentation of techniques, lazy evaluation techniques in Java by trying to apply everything that we discussed about in the context of streams. All right, so streams, one of the advantages of streams is that they provide to us for free lazy evaluation, and we're going to try to look at what lazy evaluation means in the context of stream and how it can be used to our advantage. So we are going to start with this example that we have already seen many times in our lectures. Okay, so this is the friends list of strings. We are calling a stream method on it to generate a stream from it. Then we filter all the names of friends that start with an N, and we collect them into a new list data structure. Okay, so the key to the stream's laziness and generating leveraging the stream laziness is that you start with an object, you generate your stream from it, then you have a bunch of intermediary operations, and those operations are actually quite lazy in the sense that they are not, as we're going to see, applied immediately, but only when the terminal operation of your stream requires actually a new element, then those intermediary operations get to work to produce that one element. And if it requires only one element, then these intermediary operations are only going to do enough work to generate that one element. That's the key to actually Java Streams laziness and how we are going to leverage it to make efficient computation. So let's take an example. We have a class, lazy streams. Oops, sorry about that. We have a class, lazy streams. Okay, so we are going to start by defining two static methods, length and toUpper. And these methods really do not do much more than their counterpart from the string class. Okay, as a matter of fact, they just rely on returning the result of name.length. So name is a string parameter, okay? So the length of that string parameter is just calling length from name. So we rely on the length method from the string class. And same thing from toUpper. The only thing we did really is we added a system.out.println message here and here, just so that when those operations are actually happening, we get some trace on the screen. So that's going to allow us to see easily when we run our code how often those operations are happening. And that's going to be the key to measure, whether or not we are being lazy and how lazy we are being, how many of those operations we are trying to successfully avoid performing. Okay. So that's it. Those two methods really, those two static methods are just for tracing purpose. And then we have our main method in which we are going to have a list of strings named names. So we use the good old arrays.asList static method to take a bunch of strings, put them into an array of strings, and put them into a list of strings that we can then refer to with names. And then we are going to use a stream. Here you can see the structure of a pipeline there. And we are going to use this pipeline to process a single string, that is the first three-letter names that we find in that list. Okay, so only one name, the first one that we encounter, that is made of 3 letters. So how do we compute that? Nothing very new compared to what we did in those lectures so far. So we start with names, that list of string, we generate a stream from it, then we filter out all the names that are not 3 letters, exactly 3 letters. So we keep only the names that are exactly 3 letters. For those names that are 3 letters, we map them so that we get an all uppercase version of the string corresponding to those names. Then we use the terminal operation find first. And then we use get. And the only thing really to be careful about here is when I write .get here, it might look like it's yet another stream operation, and you would be tempted maybe to say, well, everything is intermediary stream operation and get is actually the terminal string operation. Well, that would be incorrect for you to think so, okay? Find first is a terminal stream operation. And this terminal stream operation returns what? An optional. And when we call the get method, we are calling the get method on the optional of string class. Okay, so watch out. It's easy to misinterpret this because of the way it's written, but this is right here, find first your terminal stream operation, and then we are just chaining more calls on something that is essentially an optional of string. Okay, and then assuming that we always have, something that's going to be a result here. So we are kind of cheating a little bit with the concept of optional here. Really what we should be doing is get an optional and then do the name of that optional dot if present and do that system.out println only if it's present. But okay, so here we're assuming that we're always getting something in our optional. We're using get to get it out of the optional, storing it in the first 3 letters name variable here, and then we println that 3 letters name. First 3 letters name, sorry. So, what is interesting with this example is how lazy can we be? And how, more importantly, more to the point, how lazy is the Java Stream framework by default? Okay, how smart it is it? So, let's assume that our intermediary operation are not lazy. So the opposite of lazy is eager. So let's assume that those intermediary operation comply to an eager evaluation policy. This is what would happen. So the first step would be to generate our stream. Here it is. Each box represents one of the strings here. So we have 12. 12, that's it. We have 12 different strings here that are fed into a stream. And then we apply the filter operation. So eager evaluation means that we filter each of those elements. So we apply 12 times the filter operation, and we generate a stream with only 2 elements. The 2 elements would be, well, let's see, Kim and Joe, because these are the only 2 names in that list that have exactly 3 letters. After that, we have a new stream as output of the filter step here that has 2 elements. We feed that stream to the map step. So the map is going to be applied twice on each of those elements, turn them to uppercase. Then we have a resulting stream that has the same number of elements, which is common with map, okay? 2 elements, they are uppercase version of Kim and Joe. And then we apply the find first operation, and this is going to be applied only once, okay? We apply find first to the first element of the stream, and it terminates because it just needs the first element, okay? So that's going to be, end result is going to be Kim, uppercase K-I-M. Okay, so total 12 plus 2 plus 1, 15 operation to process that stream and get that result. That is assuming eager evaluation on the part of our intermediary operation. But that's not actually what the Java Stream API does for us. Okay? Instead, the Java Stream API uses lazy evaluation for its intermediary operation. So if we run this code, including the system.out.println that we added, just for debugging purposes, if we run this code like this, this is what we're going to get on the console. Getting length for Brad. So that means that the length method here that is called as part of our filter has been called on the first element. Very well. Then getting length for Kate, so it's been called on the second element. Getting length for Kim. So far it looks like we are doing exactly what we described in the previous slide, right? The filter operation is applied to every single element of the stream generating from that list of strings. Except that now Kim is equal to 3. The length of Kim is equal to 3. So what's going to happen next is we have the trace here, the system.out.println trace that indicates that the toUpper method has been called. So right now we have one element that made it to the output stream generated by the filter step. And immediately that one element has been consumed by the map step, which maps it into a toUppercase version of itself and spits it out in the output stream of the map step. Well, guess what? Immediately it can be consumed by find first, right? So find first is going to consume that element of the stream, and it's going to display it. That's what it, I mean, it's not displaying it, but it's, how to say, collecting it from the stream. But then we don't need the stream anymore. The stream can be closed because find first is a terminal operation. It received everything it needed, one element, we're done. Okay, so instead of 15 operations, we have many fewer and fewer operations here. As a matter of fact, we have 5 operations total. So the stream here from names generated things lazily. They were consumed by the filter operation, so 3 of them to reach the name Kim, then 1 map operation to map it to uppercase, and 1 find first operation to just extract it from the stream. 5 operations total as opposed to 15 and the generation of all of those elements that we didn't need actually, even in the stream. So this is why lazy evaluation is interesting. This is why it is important, okay? So all of the technique that we discussed previously about doing lazy evaluation, you know, in the context of regular Java code, if you want to call it that, you can see here how in the context of stream, because we have this concept of a pipeline of execution of different steps, that can actually yield some significant benefits in terms of performance. And all of that without us having to optimize code, without us having to worry about, you know, doing anything specific in our code. The only thing we do in our code is describe what we want the final result to be. We want a stream from names, we want to filter it, we want to map it, we want to get the first result. That's it. And the Stream API is smart enough to actually reach that result in a way that can be easily parallelized and that is also very efficient. So let's take a look now at another demonstration here to really show just how lazy we can be with the default behavior of the Java Streams API, okay? We are doing the same, we are accomplishing the same task here, we're doing the same thing. But the difference is that we store the stream resulting from the first 3 steps here, generate the stream, filter, and map, okay? So when we have done with the map, right now we still have only a stream, right? We didn't finalize it. So we are going to store this result in a stream of string named names with 3 letters. Okay, so this is the first time where we actually save in a variable a stream, okay? Generally, we just call here the terminal operation and we look at the final result. Well, here we save the stream in a variable. You can do that, just be careful. Don't be tempted to reuse that variable several times. That would be a trap, okay? So once we have this, we display on the screen mark 1. And then we use that same stream, and we can use it only 1 time for a terminal operation, okay? That's the catch here. That's why it's not necessarily a good idea to store streams in intermediary variable like that. But we call immediately here a terminal operation on that stream, which gives us an optional of string, and we call get on that optional of string to get the resulting string that we assign to the variable first, and then we display first, okay? So if we run this, interestingly enough, this is what we get. So the first thing to display is mark 1. So we have system.out.println statement inside of length. We have some inside of 2 upper, and none of them actually triggered. Okay? So that shows you really the degree of laziness here. And then only when we are trying to get actually a terminal operation executed on that resulting stream, only then that stream is going to be generated. So we are going to realize that yes, we need to get the length for Brad, we need to get the length for Kate, but none of them are going to make it past the filter step. Then we get the length for Kim, makes it past the filter step, into the map maps it to uppercase Kim, and then find first as its result. So that really shows that the streams that we generate with all of those intermediate operation, sometimes you might think, you know, well, it's wasteful for me to generate all of those intermediary data structure and then absorb them into another processing step and then generate a new one. Okay, the whole point of mutation is that we prefer to change the state of objects so we don't have to constantly recreate object. But you can see now that with a proper approach, those creation of new object all the time that are somewhat characteristic of the functional programming approach as a whole can be made fairly efficient. Okay, so you reap all the benefits of functional programming and statelessness, which is easy parallelism, easier to debug, easier to read, easier to understand and maintain. But at the same time, you do not lose as much efficiency that you might think to start off with. So now we are going to look at creating, leveraging the lazy evaluation techniques that we have been talking about to create infinite collections. So we're going to start with, and our examples are going to be numerical in nature, okay? So an infinite collection just means that we can keep calling on a collection, give me the next element. And if we keep calling, give me the next element, then it's going to never stop, okay? But that doesn't mean that we have an infinite number of elements that have been pre-computed and stored in memory. If that was the case, then we could not have an infinite collection. We would be bounded by the amount of memory we have, right? So the whole idea of combining infinite collection with lazy evaluation is that, yes, you can have the mathematical definition of an infinite collection implemented in your code. And yet, because you proceed with lazy evaluation and you generate the next element only when you need it, you don't have to have an infinite collection actually stored in memory or pre-computed, okay? All right, so let's take a look at an example, and we're going to use the prime numbers, the generation of list of prime numbers as an example. So we start with a static method isPrime, takes a number, tells us true or false whether this number is actually a prime number or not. So how do we do this? We return a Boolean expression. So the first condition for the parameter number to be prime is that number is greater strict than 1. So 0 and 1 are kind of exception there. And then, logical AND, if number is greater than 1, we further to that check that there are no divisor number between 1 and the square root of number. So this is an algorithm that you probably implemented several times in your lower level or undergraduate programming courses. The only thing we do here, we use a little bit of stream notation to do the same job. So we start here with a method of the class intStream. So you know that intStream is one of those streams that contains primitive data type. So we have a special intStream for int, long stream for long, and double stream for double, okay? So we use one of those, the intStream. The range closed method is going to take two parameters. The value at which we want the range that's going to be generated as a stream to start, 2, included, and the value at which we want to stop, not included. So that's why it's called range closed, okay? And this value is going to be the conversion into int of the square root of number. Okay, so we do a little bit of type casting. So out of intStream.rangeClose with those parameters, we are going to get a stream of int values starting at 2, then 3, then 4, then 5, etc., up to the square root of number. Okay? And then we apply to that stream, a method called nonMatch. All right? And as you would expect, nonMatch is going to return true if none of the elements of the stream on which you apply it actually match the predicate that I specify here as a lambda expression. So what is my predicate? Give me an element of the stream, okay? And I'm going to take number, which was my parameter, the number I want to determine whether or not it is a prime. I'm going to take number, try to divide by divisor, which is the number in the stream, and if I find 0, then I return true. Okay, if I find it's not 0, then I return false. And the idea of non-match is that we are going to filter out all of the elements that can be actually divided by one of those divisors. Okay? Sorry, all of the elements that divide actually are one number. So, this is pretty much a stream version, okay, of a traditional isPrime method. We could rewrite this, you know, just as you did probably in introductory programming courses, without using non-match, without using intStream or range closed, and we would have something very, very similar. We just here use this opportunity to illustrate how we can do this kind of stuff with also stream techniques, okay? But none of this is really what we are targeting in this example, okay? This is not showing us the benefits of lazy evaluation yet. It's just using stream tools instead of traditional tools. So let's continue. Now that we have an isPrime method that we wrote, in the style of streams, why not? Or if we have a isPrime method that is just written the good old-fashioned way, let's try to use it. So we have here a method primes that takes a number and returns a list of integer. Okay. So if the number that you give me tests to be a prime itself, then I'm going to concatenate that number to the result of calling primes recursively on that number plus 1. So I'm pretty much building here, and I'm returning this concatenation, right? So I'm pretty much building here a list of integer containing only prime number. So you tell me to start at number, whatever number you specified as parameter. If it's a prime number, then I put it in the list, and I test if the next number is prime, and so on and so forth. If that number is not a prime number, then I'm not going to put it in the list. It's not a prime number. But what I do is I call myself recursively to check if the next number after it is a prime number. And again, if it is, I put it in the list and keep searching. If not, I just skip and keep searching. So this code is unusual. It's a recursive code, but it's pretty clear that it's infinitely recursive code. So the way that we wrote it right now would not be really useful, okay? Because we keep actually calling ourselves recursively, we keep incrementing the value of number. Generally, when we do a recursion, right, we have a termination condition. We start with a number and we keep decreasing it until it becomes 0 or negative, or we start with an arbitrary number and we keep increasing until we reach a sentinel value, right? But here, none of that. We keep recursing forever. So this is not practically usable. But we are going to make it practically usable because this is a way to generate an infinite list of prime numbers. And if we can couple that with lazy evaluation technique, then that definition that is really simple to understand and very natural because it matches the recursion of the underlying mathematics, well, that version could be usable with lazy evaluation. So let's see how we can introduce lazy evaluation here. We are going to define our class primes. Okay. Inside the class primes, we are going to define the method primes that takes two parameters, a from number, which is where I start looking for primes, and then a count that tells me how many prime numbers I want. And then I return the list of integer that represent my list of prime numbers. So, slight variation on what we were doing before. And we introduce streams. Why? Because streams are lazy. So if we can actually integrate our idea of a recursive infinite method with streams and leverage their laziness, then we don't have even to do anything really to have this working for us, okay? The laziness of the stream will couple with the infinite nature of our recursion, and the recursion is going to be used only as needed. So how do we use stream here? Well, we use a static method of the stream class named iterate. So iterate is meant to generate those kind of, infinite streams of numbers, for example. So we call iterate. We have a new method that we are going to detail in the next slide, okay, named prime after. And the point of prime after is to return a prime that occurs after, the first prime that occurs after a number we specify as parameter. So in this case, we are going to, since we need to go to start at from number, which is a parameter here, we are going to tell it to start at from number -1, so that if from number is a prime, then it's going to be the first prime after from number -1. So we call this method that we have not yet written, and we get a first prime number occurring after from number. And that's going to be our seed. And then to obtain the second element from that iterate stream, what's going to happen is that iterate is going to call this method, prime after, but give it as parameter our seed. So that's going to generate, because this is a parameter we take here, that's going to generate the next prime after that first prime that we found as our seed. And then to generate the next one, we're going to call prime after on the previous result again. So the first time the previous result was a seed, what we used to start the whole thing with. But since we call prime after on that seed, now that's the new result, so we call prime after again on that result. So we are nesting the calls to prime after every time on the result of the previous return value from the previous call to prime after. And then we use a little trick here. We use the limit intermediary operation. The limit intermediary operation tells us, well, I just want that many elements in my stream. Okay, so we started with a seed value here. Okay, then we provided a lambda, a method reference in this case, but it could be a lambda that is a unary operator that is actually the supplier of data for our collection. Always takes the previous response, the previous result as parameter, generates the next result. Okay, and now we are saying, well, I want to continue this, but I want to not go past count iterations. Okay, so that's how we put a cap on the number of iterations. And then once we have obtained actually a stream, of the size that we wanted, then we collect it into a list of integer. All right, so the limit operator is very interesting. Okay, so we saw already the way that the stream was going to be built using that unary operator primes colon colon prime after. Okay, we feed the current seed, the seed first, sorry, to the unary operator, we get the next element, and we feed that next element to the unary operator, we get the next element, and we feed the next element to the unary operator, we get yet again the next element. So this is how this is going to work out. Okay, now the limit operation on this is going to allow us to pretty much truncate the stream. So limit is not, contrary to what you might think, limit is not actually a terminal operation on the stream. Okay, it doesn't say I'm going to consume 5 elements. No, all it says is no matter what comes into my input stream, I'm going to generate it as is in my output stream, but I'm going to keep track of how many times I do that. And as soon as I've done it, like for example 5 times, if count is equal to 5, then I'm going to close the stream. I'm going to truncate it. The stream is over. So the terminal operation that comes after that is going to see the first element go through, the second element, and so on and so forth. And if we set our limit to 5, then as soon as the 5th element has gone through, the stream is going to show that it's closed. So the terminal operation will know that it has nothing more to collect. Therefore, it's going to generate its own result and be done with it. Okay? So a quick link here if you are curious about reading more about this limit intermediary operation. Okay? Now, what we have left to do is define that prime after method. We talked about it, we used it. It's really similar to what was our first attempt. Okay, it features that infinite recursion still, but let's take a look. Okay, so prime after takes a number. We test if that number is prime. Actually, we test if the number right after it is prime. Sorry, if it is, then we stop the iteration. That's the major difference here. Okay, prime after is going to return to me the first prime number coming after this number specified as parameter. All right, so if I find the prime, I return it. If not, I keep moving forward in the list of number, in the series of numbers, until I find a prime number. Okay, so I use this prime that I already defined, and I use it to generate one prime number at a time. So when I run this program, this is what I'm going to get. Okay, so if I ask, for example, primes between 1 and 10, if I ask for primes starting at 1 and I ask for 10 of them, then this is what I get. Okay, 10 numbers that are primes starting with 1. If I ask for 100, if I ask for 5 primes starting with 100, well, there we go. These are my 5 primes that are right after 100. So now that we looked at this kind of stuff for for infinite series of numbers. There is another obvious example that is used all the time when we talk about recursion, when we talk about infinite series of recursively defined numbers, is the Fibonacci series. So the Fibonacci series, just as a reminder, Fibonacci of 0 is 0, Fibonacci of 1 is 1. And then the Fibonacci value of a number n is computed by computing the Fibonacci value of n minus 1 and adding it to the Fibonacci value of n minus 2. So Fibonacci of 2 is equal to Fibonacci of 1 plus Fibonacci 0. So I add 0 and 1, that gives me 1, that's Fibonacci of 2. Fibonacci of 3, I would add the value of Fibonacci of 2 and Fibonacci of 1. That is 1 and 1. So Fibonacci of 2 would be 3, and so on, so forth. So what we want to do is we want to try to use this approach, this lazy stream approach, to generate a potentially infinite, series of Fibonacci number, and then say, for example, well, I want the first 5, 10 of them. Okay, and only make the effort to generate those 5 or 10, even though our definition is completely recursive and pretty much potentially infinite. Okay, so to this end, we're going to use, again, the iterate feature of stream. So stream.iterate, and because the Fibonacci numbers require us to keep track of 2 numbers in a row, okay, the 2 last numbers we computed, then we are going to store these into an array of 2 long values. So that's our seed for the call to iterate right here. A new object, which is an array of long, which contains 1 and 1. Okay? And then, as we try to apply our unary operator lambda to generate the next element, what we do is we take the current element p, which is an array of 2 elements. We save the second element of that array as being the first element of a new array we create on the fly, and the second element is going to be the sum of the first and second element of that previous array in P. Okay, P0 plus P1. And if we apply that, we have sort of the opposite of a reduction here. Okay, we just keep generating new pairs of elements stored as arrays. Okay, that contains the last 2 value of the Fibonacci number series. Then we can put a limit, so we use 92 here because if we go above that, we're going to have some overflow problem. So we say let's go for the 92 first, numbers, and then for that limited stream we apply for each, and for each pair of values that was produced, we only display the first element. Okay. So remember that if you have 2 pairs, 2 consecutive pairs, like the first pair would be 0, 1, then the second pair would be 1, 1. Well, the second element of the first pair and the first element of the second pair are the same. Okay, so there's no point in displaying every element of every pair. We just display the first element of the pair and we get the Fibonacci series. Okay. And here's another example on how to do the same job using the same tool, but slightly different. Okay, so we have the same data structure here. That is an array of 2 elements. We have the same way of computing the next 2 elements, the same limit, but we compute a reduce operation after instead of doing a for each. And all the reduce operation does is really say, keep the last element. Look at the first 2 elements, keep the second. Then look at this element and the next one, keep the next one. Look at this one and the next one, keep the next one. So pretty much that reduce operation is a fancy way to get the last element of our stream. And then once we get the last element of our stream, we get its value, okay, at index 0, and we are done. Okay, so it's again an optional, so we use a .get, and we are capable like that to give the last value computed. So the limit 92 here means I want the element number 92, sorry, of my list of Fibonacci number, and here it goes. Here the 92 has a slightly different limit meaning. Sorry, it means I want the first 92 values of the Fibonacci series. Okay, so 2 slightly different illustration of how to do the job, but the key here is that we are using lazy evaluation in both cases and a potentially infinite series.